All right, so in this video, we're going to do the first half of normal distributions, which is our learning objective SA2. So you've probably heard about a bell curve or normal curve before, but it's basically one type of probability distribution. So what's important is you guys are hearing that this is talking about probability. So this normal distribution is this bell-shaped curve, which is called a normal curve, and it's normal because the key thing here is it's symmetric about the mean. So when we look at our normal distribution, we use the Greek letter lowercase mu to represent mean. And you'll see mu is right here. This is my x bar, that mean, right in the middle. So when we're saying it's symmetrical about the mean, that means if I go the same distance right or left, it's going to be exactly the same. Does that make sense? So you're thinking about, for example, parabola, right? If I go from the vertex, one to the right or one to the left, I'll still hit the same y value. So same idea here with our normal distribution. So regardless of what we do, the mean is going to be in the middle, and then we're going to move out, right, left or right from the mean. So when we draw in this curve, the area under the curve is equal to 1. Because I want you to think about this as 100%. If we're dealing with probability, then 100% of you, or whatever we're looking at, is going to be falling somewhere under that curve, because that's every possibility. So that's why the whole area is 1. Okay? So then when we look at these specific bands going from the mean, what we like to do is we like to work with our standard deviation. And here you're going to see instead of s, we have this lowercase sigma. Because this is the population standard deviation that I mentioned in the last video. It's not going to be a big deal for you guys to remember the difference, because one standard deviation is 1 over n, the other is 1 over n minus 1. But just to let you know, sigma is what we use for population standard deviation, and the lowercase s is for sample standard deviation. Okay, so how do we build this normal curve? We're basically moving standard deviations away from the mean, because remember, standard deviation was also telling us about spread, so we can see how, tall and compact your curve is, or how flatter and spread out it is, because of how far we're moving away from the mean. So things to remember right here, 68% of the entire area is within 1 standard deviation of the mean. So that means if we just go 1 standard deviation to the left or to the right, we get half of that, which is 34%, right? Then 95% lies within 2 standard deviations of the mean. So you can divide 95 by 2, and that's going to give us 34 plus 13.5, or 47.5. And that's how we can also figure out each of these little bands, because from the mean to 2 standard deviations away, that's a total of 47.5%. So if we take away the 34, we see that next band is just 13.5. And we can keep going with that. So 99.7 is within 3 standard deviations, and then the rest will be at the end. So that's how we figure out those values. And that's something you guys will want to remember, because if I'm asking you for the probability, then we were using these percentages to figure out our probability. So if you look at this example, we have a normal distribution. Really important that you see it's normal. If it's not normal, then we're kind of stuck. We have a normal distribution that has a mean, mu, and a standard deviation, sigma, and an x value randomly selected from the distribution. So that means something underneath that curve, right? We want to find the probability. So what does this mean? This is saying, what is the probability that we are 2 standard deviations to the left of the mean up to the mean, if that makes sense. So what is mu minus 2 sigma? Well, if you look at that from our curve, that is this region right here. So we want to go from that mu minus 2 sigma here. Well, I can write that a little bit better. Let me scoot up a bit. So we're going to take that mu minus 2 sigma, right, all the way up to the mean. So the mean is right up here, so that is mu. So we're asking, what are the chances we lie in this shaded region? Well, then you have to think, okay, well, what is that percent? So if we look at this, we know mu minus 2 sigma up to mu minus sigma is 13.5. So I can take that 13.5% right? And I'm going to add that to this band here from mu minus sigma to mu because I want to add in that second piece. So that's going to be plus 34%. So we can convert that to decimal values, 0.135 plus 0.34, and that's going to give me a probability of 0.475 or 47.5%. And again, we don't even need to worry about what is the mean, what is that standard deviation. We're just thinking about where it falls in deviations away from the mean. Are we just going 1 away from the mean? Then it's 34. Are we going 2 away from the mean? Then we'll do 34 plus 13.5. All right, so again, what's crucial is you want to think about what the notation means. So here, we're looking at just, okay, in general, if x is less than mu plus 2 sigma. So what does that look like on our curve? Well, if this is my bell curve, here's my mean. Mean plus 2 standard deviations is going to be out here. So there's my mean plus 2 standard deviations. And there's no lower boundary. That means we're looking at everything here to the left of mu plus 2 sigma. So I can look back at my chart here and say, okay, here's mu plus 2 sigma. I'm going to add every single one of these values to the left of it. So that's your 13.5%, right? 34%, another 34%, 13.5%, 2.35%, and 0.15%. And let me actually rewrite that so it's a little bit neater, and then we'll just add up our decimal values. There you go. Slightly neater, but fit it all in. So we're just basically adding all of that. Now, one thing I want you guys to realize is, well, what's so important about that mean? Well, that cuts our distribution perfectly in half. So what's half of 1? 50%. So if we're just looking at everything up to the mean, that's actually 50%. Oops. I wrote that all funky. So that's going to be 50%. So that means here we just have 13.5, 34, and all of this is really just 50%. So we can use that, not really as a shortcut, but just using that idea of what the mean means, right? And where that falls in our distribution, we can kind of save ourselves a little bit of time and a little bit of addition. All right, so I'm going to go ahead and add this up. This is 0.135 as a decimal, plus 0.34, plus 0.5, because that all is going to be 50% of my data, to give me a probability of 0.975. So 97.5% chance, right, of picking an X value in that giant region. So that's our normal distribution. Okay, so here's another example of how we can use our normal distribution. Let me scooch this up. So the scores for state peace officer standards and training tests are normally distributed. So remember, look for that in the directions. Normally distributed is a huge clue. Hey, let's work with our normal distribution. With a mean of 55 and a standard deviation of 12. The test scores range from 0 to 100. So now we have to think, okay, it's actually giving us these values. We can build our own normal distribution. So as with everything, it's great for you to label what we're working with. So we're dealing with test scores. So I'm going to put test scores here. Oh, sorry, I don't want to use that highlighter anymore. I'm going to put test scores here. And kind of make, you know, a little x-axis sort of thing to represent what that is. Okay? And then what's important here is we want to build our curve. So remember, the middle is that mean. So I'm going to start by putting 55 right here in the middle. Okay? And then in general, we know it's a normal distribution, so you can make your bell curve and try to be as symmetrical as possible. Really rough for me because I'm working on a tablet, but you want it to almost look perfectly cut in half, right? Let me try that one more time. Right, peaking at the mean. All right, so that's probably as good as it gets for me. And then what's important is you always want to give me those specific bands. So we want to go up to 3 standard deviations from the mean, right? So here we're going to do mean plus 1 standard deviation. Then we're going to do mean plus 2 standard deviations. Then we're going to do mean plus 3 standard deviations. And then we want to do the same thing on the other side. So now we're going to the left, so we're subtracting. So this will be mean minus 1 standard deviation, mean minus 2 standard deviations, and finally, mean minus 3 standard deviations. Okay, so we're going to start with that 55. 55 plus 12, 67. 67 plus another 12 is 79. 79 plus 12 gives me 91. And then go backwards. 55 minus 12, 43. 43 minus 12 is 31. 31 minus 12 is 19. And there is my normal distribution. Okay? And then we can use this to help us figure out percentages or probabilities based on what we remember. So remember, within 1 standard deviation is 68, 2 standard deviations, 95, 3 standard deviations, 99.7, and then we can divide those in 2 to figure out, and subtract, right, to figure out each of these bands. Okay? So, if we take a look at this, what percent of the people taking the test have scores between 43 and 67? So first we have to ask ourselves, well, what's 43 and what's 67? 43 here is the mean minus 1 standard deviation. 67 is the mean plus 1 standard deviation. So we're looking at just this part, right? If this is my curve, this is my mean, I'm just looking from mean plus or mean minus 1 standard deviation and mean plus 1 standard deviation. Sorry, that's really messy. But if we want to think about that, we're like, where have I seen that before? Let's scroll back up. Right here, mean minus 1 standard deviation all the way to mean plus 1 standard deviation is 68%. Or if you remembered all of these individual values, which actually might be more useful, is we're going left 34, right 34, 34 plus 34 is 68. So we're just going to say that about 68% of the people taking the test have scores between 43 and 67. Okay, let's look at the second part of this question. So an agency in the state will only hire applicants with test scores of 67 or greater. About what percent of the people have test scores that make them eligible to be hired by the agency? So the first thing I like doing is I like to think, okay, well, remember, what does that number mean? So we said 67 earlier. That's mean plus 1 standard deviation. And if I'm looking at this, I'm like, okay, here's my normal curve. Here's the mean plus 1 standard deviation. And we're saying we want anyone who has that or higher. So it goes on and on and on, right, until this entire curve ends. So I'm like, hold on, there's no end. How do we even do this? Well, remember what we were looking at before. If this is the mean, everything from here on to wherever it ends is 50%. So if I just take away this empty space from 50, I'll get what's left over, right? And remember, that is just your 34%. So to do this problem, all we're doing is we are doing 50% minus 34%, so 0.5 minus 0.34, which is how I get 0.16. All right, so that means just 16% of those people taking the test would be hired based on this criteria that we have to be 67 or greater. All right, and there we go. So that is the answer. I forgot to mention earlier, you want to make sure you see the direction set about what percent, which is why I'm answering in percent. Typically, if I ask for probability, I do rather have it in a decimal or a fraction, but try to be consistent, especially if it does specify what format we want. So next, there are some U-try problems, which if you want to pause right here and do them, go for it. We're going to come back and check at the end like before. Otherwise, if you like to move on, I'm just going to scroll down and we're going to finish the last part of this video, which is talking about distributions that may not actually be normal. Okay, so what happens if our distribution is not necessarily normal? So we have 3 histograms here to kind of give us an idea of what possibilities we have. So first we have this normal distribution. So it's bell-shaped, right? It has a normal distribution. It looks relatively symmetrical from the mean, right? So we've got a nice bell shape right here. Versus if you look at the second histogram, we call this skewed left. Why is it skewed left? Because there's a longer tail here on the left. So you can see how it's much longer this way going to the left. The mean is more toward the left, right? It's on the left of the median. So here the mean is less than the median, it's to the left. It does not have a normal distribution. And our third depiction here on the right is what we call skewed right. And you can see this is basically the opposite of skewed left. So in this case, we have a much longer tail going to the right, right? It's tapering off toward the right. It's a much steeper decline on the left. And our mean is to the right of the median. So the mean is actually greater than the median. So we get a skewed right distribution. So what we want to do is we just basically want to visually identify if the histogram, right, appears to have a normal distribution. So we're thinking, is it pretty symmetrical? Is that mean, median about the same? Is our mean going to be less than the median? Do we see that kind of longer tail on the left or a tail on the right for it to be skewed left or skewed right? So if you take a look at this example, if we look at this first one, I'm looking at it and I'm like, well, if you look, it looks relatively normal. There's no one longer side on the left or on the right. There's no steeper decline on one or the other. It looks pretty symmetrical. So I'm going to say this is bell-shaped, right, and fairly symmetric. So it is approximately a normal distribution. Okay, so now let's compare that to the one on the right. So again, if I just draw in this curve, you'll see, hey, this is looking like there's a lot more here on the left side. So there's more data there. It's tapering off here toward the right, which makes it look like this skewed right distribution where we see that it's tapering off to the right. So we can say this is not approximate a normal distribution. It's skewed right. So it just isn't going to work. So there we go. So that talks about skewed left, skewed right, and how it compares to the normal distribution. You've got a couple more U-try problems to work on, so if you want to pause right here and just kind of look at those distributions, then you can resume when you're ready to check. So I'll go ahead and write those answers, and again, keep going once you're ready to check your U-try problems. We'll go back to the normal distribution problems, and then come back to these skewed left, skewed right problems. Okay, and these are the answers to the normal distribution questions earlier. So with each one of these at the top, you can see how we're just basically reading that off your normal distribution, right? So going to the left or to the right of the mean is 50% or 0.5. And then here going right 2 standard deviations away, we're doing 34% plus that excess piece, right? This 13.5%. And then so on, right? Hopefully you saw there was kind of a trick question in there. There are limitations to just looking at full standard deviations away from the mean. So if we're trying to approximate at least 75, we're like, wait, that doesn't fit anywhere. We can just kind of ballpark it somewhere between, you know, the mean and 1 standard deviation away, but we're not exactly sure. So we're gonna look into that a little bit later, but just make sure you see there are limitations to what we're doing now, okay? So those are the answers to the normal distribution. Again, please ask if you have questions. And then the last few, so we just had those last 3 left, and you were just talking about, could it be approximating a normal distribution? So hopefully you saw the first 2 pretty clearly skewed to the left. This last one might have been kind of up in the air, but it does make a relatively bell curve shape. Remember, this is an approximation, so it doesn't have to be perfectly symmetrical, but there's no like very clear skewing left or right. So that's why we'd say, okay, that's pretty bell shaped. So we can approximate it as a normal distribution. Okay, so that wraps up this first part of SA1. We'll finish the rest of it next time. Please, again, remember if you have questions, don't hesitate to ask. Thanks for listening.